In a prior screencast, we discussed the concept of a semi-infinite solid. We started by making a few assumptions, the first of which is there was no heat transfer in the vertical direction, nor was there any heat transfer into and out of the screen. We also assumed that there was no thermal energy generation, and then made the assumption that the thermal conductivity was independent of temperature. We then used the definition of the thermal diffusivity to arrive at the following partial differential equation. Because this equation is second order with respect to temperature and first order with respect to time, we need to define an initial condition and then two boundary conditions. The initial condition is that the temperature of the solid is some known value at time equals 0 for all values of x. And then the first boundary condition, we said that the temperature remained at this initial value really deep into the solid for very large values of x, approaching infinity, and this applied for all time. The second boundary condition we talked about in the last screencast was that the surface temperature was a fixed value at x equals 0 for all values of time. So the solution to this partial differential equation, subject to the initial condition and these two boundary conditions, led to the following equation that gave us temperature as a function of both time and position. However, there are a number of different boundary conditions that we can apply to model different forms of heat transfer in semi-infinite solids. In this screencast, I'm going to show simulations associated with 6 common scenarios. This is the first of which we've already discussed, in which the temperature at the surface is a fixed value, but we'll also discuss a scenario in which the flux is fixed at the surface, another one in which there's convective heat transfer, one in which there was a burst of energy at time 0 at the surface, and then the surface remains adiabatic after that. We'll also talk about a temperature at the surface that oscillates sinusoidally over time, and then we'll look at heat transfer between two semi-infinite solids that just touch each other at time 0. So let's look at the first simulation in which the temperature at the surface is some known value, and we'll call it Ts, and that occurs at x equals 0. So what you're looking at is an arbitrarily high temperature at the surface. The colors run from red being the hottest temperature, blue being the coldest temperature, and the white is halfway between the hot and the cold. Pay attention to just how fast the temperature diffused right at the beginning, and now how much more slowly it diffuses towards the end. The temperature gradient on the left-hand side just becomes smaller and smaller as that layer of red widens. In this second scenario, we're going to change the second boundary condition. So instead of saying that the temperature is some fixed value at x equals 0, we're going to look at a case in which we add a known heat flux at x equals 0. So instead of the temperature being constant, we're going to say that the heat flux at x equals 0 is some known and constant value. So in this case, the second boundary condition is q double prime is equal to some constant value at x equals 0 for all time. Mathematically, this says that the temperature gradient dt dx is equal to this known value of flux divided by the thermal conductivity. A scenario like this might occur, for example, if there was a flame or something like that, and the flame imparted, I don't know, 1,000 watts per square meter at the surface. Another scenario might be frictional effects. There might be another surface rubbing over this one with a certain pressure, and there's a frictional force, and it might move over it at a certain speed. That would also impart a steady heat flux over time. And you could use that to model the temperature as a function of time for any position of x. The solution to this partial differential equation subject to these two boundary conditions is different than the first scenario. The first thing, if we examine the form of this equation, if we consider x going to infinity, we'll find that e to the negative infinity will go to 0, and that term will drop out. The error function of infinity is equal to 1. 1 minus 1 is 0, and we're left with t is equal to t naught deep into the solid. If we examine the temperature at x equals 0, e to the 0 is equal to 1, the error function of 0 is equal to 0, and x equals 0, that second term drops out, and what we're left with is the temperature is equal to the initial temperature, and it increases with the square root of time. Note that this means that the temperature, according to this model, will go to infinity as time progresses. It won't remain at some upper value. So strictly speaking, in reality, a scenario like this could never occur. You'd either melt or burn out the solid, or there would be some radiation back into the surroundings, or some other convective effect that would take place. So this equation does have its limitation. So what you're looking at is the same color scheme as before, except now we've got a constant heat flux at the surface. One thing to pay attention to is that the temperature at the surface, instead of being that fixed red, is now increasing over time. It increased from blue through white and now up to some red value. And do remember that the temperature in this case will increase to infinity. It's increasing with the square root of temperature, which is one of the major limitations of this type of model. In a third scenario, let's consider a convective boundary condition, where we've got some fluid out here to temperature T infinity, and the flow of the fluid results in some heat transfer coefficient. So we've got some, in this case, some warm fluid that's blowing over the surface of it, such that convection occurs at x equals 0. Mathematically, we'll write this expression as the flux is equal to the heat transfer coefficient multiplied by the temperature at the surface minus T infinity. Note that I need to use a negative sign in front of this expression, because if the temperature at the surface at this location, if that's hotter than T infinity, we'll find that the flux flows out of the hot solid into the cooler surroundings. So if the quantity in the parentheses was positive, we'll have heat flowing to the left, so there does need to be a negative sign in front of that. And this flux is, the convective flux is equal to the conductive flux in the solid itself. So right at the surface, the conductive flux has to equal the convective flux. When we solve for the temperature gradient dt dx, we'll find that that's equal to h over k multiplied by t minus t infinity. And this applies only at x equals 0. And this is the solution to the partial differential equation subject to these two boundary conditions. If we examine the form of this solution, if we examine, for example, when x goes to infinity, the error function of infinity is equal to 1, so both of these first terms cancel out. Let's see, the error function of, again, infinity is equal to 1, so this term cancels out. Note that although the exponent of infinity, of course, is infinity, the rate at which 1 minus the error function of infinity overwhelms it, we find that the whole term in the square brackets goes to 0, and we're left with t is equal to t naught, again deep in the solid. If we consider the temperature at the surface of our semi-infinite solid where x equals 0, the error function of 0 is equal to 0. This term in the exponential will drop out, and the error function in this term will drop out, and it almost appears as though the temperature will go to infinity because time goes to infinity in the exponential. However, the error function of infinity is equal to 1, 1 minus 1 is equal to 0, and unlike the first case in which we fixed the flux at the surface, we'll find that the temperature at the surface will asymptotically approach T infinity. It does so because the entire term in the square brackets asymptotically approaches 1. This makes intuitive sense because the surface of the wall, of course, could be no different than the temperature of the fluid itself in the ball. So for long periods of time, this is a more realistic way to model a semi-infinite solid than it would be if we were going to assume a constant flux. So here we have a simulation with a convective boundary condition at the surface. It's not going to look a whole lot different from the case in which we have a constant flux at the surface, but do bear in mind that the temperature at the surface won't continue to infinity. We see it get redder and redder, but as time elapses, it will asymptotically approach T infinity. And you could see that from the boundary condition 2 there, which applies at the surface. As the temperature at the surface becomes closer and closer to T infinity, the temperature gradient eventually becomes 0, and the temperature will taper off at T infinity. In this fourth simulation, we're going to assume that there's a burst of energy at time equals 0. And after time equals 0, we're going to assume that the surface itself is adiabatic. This might occur, for example, if there's a real quick laser pulse that hits the surface. Examining the form of this equation, this is the energy imparted per square meter of surface area. And that's a known quantity. Maybe it's something like 1,000 joules per square meter or something like that. If we examine the form of this equation, when x goes to infinity deep into the solid, e to the negative infinity goes to 0, and we'll find again that the temperature is equal to T naught. If we evaluate the temperature at the surface where x equals 0, e to the 0 is equal to 1, and what we'll find is that the temperature will decay with the inverse square root of the temperature. So over a period of time, the temperature will eventually decay back down to the initial temperature. So the color scheme I used in this case was white for the low temperature and red for a high temperature. And when the burst occurs, we see a huge temperature at the surface, and that temperature slowly diffuses into the bulk. One thing to keep in mind is that the temperature gradient is equal to 0 at this point, and as time progresses, we see the temperature become more and more spread out. In this fifth simulation, we're going to look at a boundary condition that oscillates sinusoidally over time. It oscillates between some high temperature and some low temperature, and it oscillates about T0. Note that there's no real initial condition for this scenario because we're going to oscillate indefinitely, either forward or backwards in time. There's no such thing as, really time zero. So there's no initial condition associated with this. But we do have two boundary conditions. The first of which, again, is that T is equal to T0 deep into the solid, and the second boundary condition is a sinusoidal oscillation. It oscillates about the average temperature between the maximum and minimum, and then delta T is the difference between the temperatures divided by 2. If we examine the form of this equation, as x goes to infinity, e to the negative infinity is 0, and we're left with T again is equal to T0 deep into the solid. At the surface where x is equal to 0, we find that e to the 0 is equal to 1. This term drops out, and we'll find that the temperature oscillates sinusoidally, again about time, according to the second boundary condition. In this simulation, I've got red being the hottest temperature and blue being the coldest temperature. Purple is midway between the blue and the red. What we see is the oscillatory nature of the temperature at the surface, and what we also see is that the temperature diffuses as it penetrates deeper into the solid. It becomes more and more uniform. We see on the right the temperature at the very right edge, or as x approaches infinity, approaches some constant, which is equal to T0. In this last scenario, we're going to examine a case in which there's two semi-infinite solids that are touching each other, and we'll call these solid A on the right and solid B on the left. In this scenario, solid B is hotter than solid A, and at time 0 they begin to touch and heat transfer occurs. In this case, it will flow from B into A because B is hotter. The solution to this scenario will have two temperature profiles. This one this one is valid for x greater than 0, so this represents the temperature in solid A. The second one is the temperature for x less than 0, representing the temperature in solid B. What's interesting about this scenario is that there is a temperature at the interface, we'll call it Ti, and that consists of the ratio of several constants. So this tells us that the temperature at the interface remains steady over time. It's some fixed value. If solid A and solid B were equal to one another, we would find the ratios within the square roots approach 1, and we'll find that the interfacial temperature is just the sum of the two temperatures divided by 2, which is simply the average of the two temperatures. What's also interesting about this scenario is that there's going to be a discontinuity in the temperature profile. The temperature profile changes abruptly between solid B and solid A. However, we'll find that the flux leaving B is equivalent to the flux entering A. The reason for the discontinuity in the temperature gradient is because the thermal conductivities between B and A might be different. So in this scenario, the two materials are the exact same materials. They have the same physical properties. Their temperatures are just different. Red is the hottest temperature, blue is the coldest, and white is the temperature right in the middle. Examine right when the two surfaces touch just how quickly flux flows from left to right. The temperature right in the middle is simply the average of the two because their material properties are the same. In this case, the two materials are different. I've got a much higher thermal conductivity on the right-hand side than I do on the left-hand side. When the simulation starts, compare the uniformity on the right-hand side due to its higher thermal conductivity than that on the left-hand side. Another thing to note is that the temperature right at the dividing line does remain the same, despite the fact that the temperature profile across both is asymmetric. And do recall the flux leaving the left solid is equal to the flux entering the right solid.